Okay, cool. So I think it is time to start. So thanks everyone for coming back bright and early on the last day. Today I'll be continuing the theme of populations and astrophysical inference from stellar mass CBCs and talk about some of the emerging lessons that we've learned from our catalog of gravitational wave events. So if you remember last time, which was yesterday, we learned about some proposed evolutionary pathways to merging black holes. These are often called formation channels in the literature. They're kind of these two broad umbrellas of isolated and dynamical evolution. And then you can also add gas, which can make things more complicated and more exciting. And we went through some of the astrophysics involved in things like common envelope versus stable Roche-Loeb overflow and chemically homogeneous evolution. We talked about dynamics in dense star clusters like globular clusters and nuclear star clusters. And so today, I'll be telling you about how we might actually distinguish which of these formation channels are contributing to the observed gravitational wave population and learn some of the uncertain physics that is involved in these different formation channels or evolutionary pathways. And feel free to ask questions at any time. So yesterday I kind of left off pretty rushed and didn't get to tell you a lot about the concrete predictions that the different formation channels predict. And so today I'll be telling you about those and then also comparing it to what we've learned by fitting the gravitational wave population. So as far as predictions for black hole spins, this is kind of the original way that people proposed about how to distinguish like the broad class of isolated binary evolution versus dynamical assembly. And so the main prediction is for spin orientations. The idea is that exchanges in dense star clusters, so in the dynamical assembly channel, tend to randomize spin orientations. And so, for example, there's this paper by Carl Rodriguez and others from 2016 that shows this. So I'll explain more, but if you remember what this effective in-spiral spin is, this is basically this on the y-axis here is the fraction of events with negative chi effective, which means that there's at least one spin that is misaligned by more than 90 degrees. And essentially, if this is 50%, that means that you have isotropic spin orientation. So isotropic spin orientations create this black line here, which is just at all masses, you have 50% of your systems with negative chi effective. When you have isolated binary evolution, that because the stars have lived their whole lives together, there's a lot of processes like tides and accretion that tend to align their spins. And so if the black hole spins are inherited from the rotation of those progenitor stars, then one of the main ways to misalign spins is through the natal kick that the black holes receive from the supernova that gives rise to them. And so in this paper, they assume different prescriptions for natal kicks. Maybe natal kicks are stronger for low mass black holes, which are still explode as a supernova versus the higher mass black holes, which maybe don't really explode. So there's none of this asymmetric ejection that leads to natal kicks. And so maybe you can have some much smaller fraction of negative chi effective at lower masses compared to higher masses. And again, this is uncertain from isolated binary evolution, but it is still a pretty small number, most on order 10% of these very misaligned spins, misaligned by more than 90 degrees, compared to in dynamical assembly, for the most part, the spins don't really care about what the spin orientation of the partner black hole is, and so they can just be isotropic. There was this recent paper, however, from earlier this year by Foglia, who actually found a way in dense star clusters where you could break the isotropy of the spin orientation. So you can ask Foglia about that. And I think she had a poster on this as well. But the basic idea is that if your binary black hole is actually, there's a massive star that is colliding with the binary, then that star is providing some gas material that can be accreted onto those black holes and align their spins. And if this happens, when the binary black hole is still in a pretty tight orbit, then it can merge in that aligned spin configuration before a third black hole comes in and does an exchange, and they forget that they used to have aligned spins pretty much. So these systems in the triangles here can actually merge with with positive aligned spin, preferentially positive aligned spin, because they got that from this massive star colliding with the binary. So that's just a caveat from the rest of what I'm going to tell you, which assumes the more traditional picture that dense star clusters lead to isotropic spins. So keep that asterisk in the back of your mind. Okay, so these are the different general predictions for isolated versus dynamical assembly in terms of the spin orientation statistics. So there's this nice graphic here, which I showed, I think, yesterday as well by Shanika Gauladaj, which kind of illustrates this in isolated binary evolution. The two black hole spins tend to be aligned with the orbital angular momentum, and in dynamical assembly, they're just kind of random. So in terms of the effective in-spiral spin, if you remember this picture of the geometry in the back of your mind, and just to remind you that this chi-effective parameter is defined as the mass averaged, the mass weighted average of the two black hole spins projected onto L, the orbital angular momentum axis. And so if you have negative chi-effective, that implies that at least one of these black hole spins, it has a negative component on L. So it is tilted, and the tilts here are defined by theta. So it's tilted by more than 90 degrees. And so as we saw from the Rodriguez 2016 paper, for example, that is easier to accomplish via dynamical assembly than from isolated binary evolution. That's like the sort of accepted picture in the field right now. Meanwhile, isotropically oriented spins imply that the chi-effective distribution is centered at 0. So 50% of your binary black holes will have chi-effective less than 0 and 50% greater than 0. And so, okay, what have we actually learned by measuring the chi-effective distribution from our gravitational wave events? And so this is using the 70 or so binary black holes from the third gravitational wave transient catalog published by the LIGO-Virgo-Cogra collaboration. So here is the cumulative distribution as a function of this chi-effective parameter. And so you can see the 50% line. So if we had an isotropic distribution, we would expect the 50% of the spins to be negative and 50% positive. We actually see that the median here, this 50%, is a little bit positive. So it is not consistent with an isotropic distribution. But we also see that some black holes have tilts larger than 90 degrees. And maybe these are, this doesn't require large negative spins, but it is a non-zero fraction, seem to have spins as negative as negative 0.05 or negative 0.1. Yeah.
Can you explain what is the data?
Oh, yeah. So this is fitting a model to the mass spin redshift distribution of binary black holes in terms of the spins are fit in terms of this chi-effective parameter. And so here it's marginalizing over, the mass distribution, the redshift distribution, and just for fun, there are two separate models. So one is fitting a Gaussian distribution to chi-effective, and here it's just that cumulative distribution. So this is fitting for the mean and standard deviation of chi-effective in the population. This is a mixture between a Gaussian and a flat distribution. I think this was inspired by one of Javier's papers, if I'm remembering correctly. Yeah, so does that answer your question? And then this is like the median and 90% credible bounds on the cumulative distribution as a function of chi-effective.
So you had a conclusion that there is some support for negative spin.
Yeah.
And I don't understand how based on it you get that.
So if there was no support for negative spin, then then basically at 0, it would be consistent with the cumulative distribution being 0. So like the fact that there's no support here. And it's hard to tell from plots like this. So there's other tests you can do to fit for basically the fraction of negative chi-effective here is, inferred to be 0.2 plus or minus 0.1 something. So this fraction that's smaller than 0 excludes 0 according to this plot. Okay, so, and there are other, and this is, of course, these is just two models. There are other tests that people have done to look at how robust this claim is that we actually have systems in the astrophysical population with negative chi-effective. Okay, so again, assuming that clusters make isotropic spins, this kind of implies that clusters produce some but not all black hole mergers because this distribution of spin tilts is not isotropic. But you might, believe Fulia's paper, which says this is actually perfectly consistent with clusters, but that paper wasn't out when we did the study. Okay, the other thing that can happen in these dense star clusters where you have dynamical assembly, as I alluded to yesterday, sometimes it's pretty rare for most environments, but sometimes you actually have your black holes merge and the merger remnant stays in the cluster. It doesn't get kicked out of the cluster. And so when that merger remnant stays in the cluster, it can go on to merge again with other black holes that are around. And we call this sort of repeated merger scenario hierarchical mergers. And this is something that is generally predicted for the densest stellar environments like nuclear star clusters, AGN disks, potentially the densest globular clusters. Also, the thing to note here is that you just need the escape speed of the larger the escape speed of your environment is, the easier it is to retain the black hole merger remnants. And so the easier it is to have a significant population of hierarchical mergers. whereas a lot of channels predict only first-generation mergers, right? So in isolated binary evolution, you have these two black holes in the galactic field. They merge with each other. They're really far away from any other black hole, so they're never going to experience another merger. And so hierarchical mergers, well, in case it's not clear, here's another cartoon. We often refer to these as the first-generation mergers are the ones born directly from stars, and then second-generation mergers are the ones born from a previous merger, and they can go on to merge again with another second-generation or 2G black hole or another first-generation black hole. So every time we see a gravitational wave event, we know we can ask, is it the first time those black holes are merging, is it a 1G plus 1G merger, or are we seeing the gravitational wave signal from a 2G plus 2G or 1G plus 2G or higher generations as well? And so so one concrete prediction from hierarchical mergers, in addition to, the black holes are more massive, because when you merge two black holes, you make a more massive black hole, is the prediction for the spin. And so the second generation black holes that are born from a previous merger of first generation black holes tend to spin at a dimensionless spin magnitude of around 0.7. And there's some additional features here imparted by the escape velocity of your environment. This was recently studied in a paper by Angela Borchers, who's a finishing PhD student at AEI Hanover, for example. And so here you could see the spin of the merger product, and this is the distribution of spins. And so this is the canonical 0.7 value. You can see this distribution is sensitive to the escape velocity of your environment, and that is simply because that having a finite escape velocity is going to select for different configurations of initial black hole spins. Like aligned spins will receive smaller gravitational recoil kicks than when you have spins in the plane. And so that's why when you have smaller escape speeds, you're selecting preferentially for those aligned and anti-aligned mergers. So the distribution has more support here and here, for example. But if you squint at this compared to current measurement uncertainties, this is basically just 0.7. So we can look for spins of 0.7 in our inferred gravitational wave population and try to measure the fraction that are hierarchically assembled, especially if we remember that if hierarchical mergers are dynamically assembled, the spin tilts are randomly oriented, at least in the canonical dense star cluster environment without gas. And so this means that we expect a fixed fraction of hierarchical mergers to have moderately large misaligned spins. And so we can, kind of go back to our cumulative distribution of chi-effective. This is not what we measure. This is the predictions from hierarchical mergers, right? Where your chi-effective distribution is still centered at 0, 50% below and above 0. But then the chi-effective distribution has to be pretty wide because the black holes now have larger spin magnitudes. So they extend to larger positive and negative values. And this is for if you have two second generation black holes versus a first generation and a second generation black hole. So a lot of people have studied this. Okay, and so now we can compare this back to the inferred chi-effective distribution. And I showed you already in the first lecture this result that recently came out by Fabio Antonini, Isabel Romero-Shaw, and Tom Collister, with this follow-up work by the same authors and some others. So I think this is a super exciting result just from observations that are already several years old at this point. But they found this evidence that the chi-effective distribution, so this is the log of the standard deviation of the chi-effective distribution. So it's a measure of how wide that chi-effective distribution is. as a function of the primary mass of your black hole. So you see that, well, this is a very flexible model. So at very low masses, there's just not enough data and it can be whatever. At these kind of intermediate masses between 10 and 40 solar masses, it's constrained to be very, very small. So very narrow chi-effective distributions, not a lot of support for large spins. But then above 45 solar masses, it jumps up and the chi-effective distribution becomes wider. And so this standard deviation that is inferred up here for the chi-effective distribution at these higher masses is consistent with hierarchical mergers, the spins that you would expect from second generation or maybe higher generation mergers, whereas the mean of the chi-effective distribution is also starts to be more consistent with zero at these higher masses. So an isotropic distribution at higher masses. So above 45 solar masses, it looks like the data is preferring a spin distribution that looks like what we get from hierarchical mergers. And that transition is relatively sharp. It seems like down here, not a lot of hierarchical mergers are contributing to the population. And then at these higher masses, they are. Yeah.
So let's say that about 40 is hierarchical mergers. This means that those 40 are both being assembled in a cluster, 220s, and so why then does those 220s have a mu, the mean of the chi-effective component?
Yeah, so
Is the rate fine, like if I think it goes 40, then there is an implied 20, 20, or is that?
yes, so I don't think anyone has done the detailed rate argument here. I think only 1% of the astrophysical rate is above 45 solar masses. So I don't think the rates are going to be a problem. And my interpretation is, yeah, if you have hierarchical mergers up here, then definitely some of the ones down here are going to be dynamically assembled, but you could get contamination from isolated binary evolution also down here. But yeah, I don't think, and another thing to keep in mind is that you wouldn't get, you also have 10 solar mass black holes in clusters. So some of the 20 solar mass black holes, like if you have 50 solar mass black holes that are hierarchical mergers, you're also going to have 20 solar mass black holes that are second generation mergers. And so that's another prediction from, actually the simulations of clusters predict that most second generation mergers will be the low mass ones. So that should also contribute here. But yeah, I'll show later on what we can actually learn about clusters from comparing some of these rates, but not in this detail, which will provide a lot more information. Yes.
This is not chi-effective. This is not a distribution of chi-effective. This is the uncertainty on the sigma inferred.
This is the width of the chi-effective distribution. Each.
Spread in this curve is not the spread in chi-effective.
Yeah.
Uncertainty in the inferred sigma chi-effective.
Yeah.
So that is blowing up is just saying that there is not enough data on the right.
Exactly. Yeah, exactly. So down here, the chi-effective distribution could be super narrow or it could be super broad. We just don't have enough black holes smaller than 10 solar masses. Oh, yes. So here above 80, the chi-effective distribution could be very narrow or very broad also. It's just that in this range, we're excluding chi-effective distributions that are very narrow. So that's what this this curve here is kind of like the smallest width of the chi-effective distribution at these masses. Cool. Okay, so well, I think that result is very exciting also because, you know, it's showing that maybe there are hierarchical mergers in the population. That kind of implies some dynamical origin, I think way more robustly than, you know, having spin tilts misaligned by more than 90 degrees. But the location of where this like spin transition happens, so where this distribution seems to go from narrow chi-effective distribution to broader chi-effective distribution at around 45 solar masses, hints at this being what's called the lower edge of the pair instability mass gap. And I think we've heard about pair instability supernovae in some different contexts, but just to get everyone on the same page, if you haven't learned about pair instability before, so the idea is that for stellar collapse, so for the first generation black holes that are made directly from stars, we don't expect there to be any in the range from around 50 to 130 solar masses, because what happens is when you start to dial up the core, the carbon-oxygen core of those progenitor stars, initially, you know, you have a larger core, so you have a larger black hole mass. They kind of scale with each other. The different colors here are just different metallicities. But then at some core masses, your star starts to experience these pulsations. And then at even higher core masses, the star experiences this pair instability supernova and doesn't leave behind any black hole at all. So the remnant mass is 0. There's no black hole left behind. The reason for that is that you have this very, very massive, very hot carbon-oxygen core that is, you know, the gravity is pulling in. There's photon pressure that is providing support against gravity. At this temperature range that's reached in these very massive cores, the photons start to spontaneously produce electron-positron pairs, which don't provide the pressure support. You have these sudden contractions, which causes explosive oxygen burning, and that can inject enough sudden energy into your stellar core that it entirely disrupts as a pair instability supernova, or at least causes these pulses that shed off like tens of solar masses at a time. So it seems like we shouldn't have any first generation black holes made from stars between this range, starting at around 50 solar masses, which kind of makes sense then that at 50 solar masses, it's consistent with all of these black holes being second generation black holes, because we actually wouldn't expect first generation black holes there from stars. So that's kind of exciting, I guess, to put that simpler. If you remember this mass distribution that I showed in the first lecture, again, around 1% of these primary black hole masses are above 50-ish solar masses. And this is kind of where the Antonini et al. Papers identified that there's this transition in the spin distribution. And so this is consistent in terms of spins with being the lower edge of the pair instability mass gap. Okay, oh, yes.
This bomb is just before the start of the
Oh, yeah. Yeah, so this bump, we originally thought this bump was the signature of the pulsational pair instability supernova, right? Because if you look back at this plot, this is showing that there's a wide range of core masses that is going to produce black holes at around the same mass. So there should be some pileup in the mass distribution before the lower edge of the gap. But then we kind of measure this bump to be at around 33 solar masses, which then, so also this plot is also kind of, I mean, yeah, that's from 2020, which I guess is kind of old at this point. And so it's like in this paper, they were finding that this, that this black hole mass gap could start at around 45, like below 50 solar masses. Now the stellar evolution people are saying that it should actually start at like 70 and above solar masses. And that means that this is, before this evidence came out for the spin transition, they were saying, well, this is actually too low to be pulsational pair instability supernova. But now I think that this is starting to look like the edge of the pair instability mass gap, which to me does make this seem like it could be the pulsations, but I don't want to get in trouble with the stellar theorists. So, okay, so that is what I want to say about spins for now. I guess the other, well, I will come back to spins a bit, but the other thing that I won't really talk more about, but I think probably a lot of you here are thinking about eccentricity, and I think this is a very exciting emerging direction also, because eccentricity measurements are going to probably be way more informative than spin orientation statistics to determine whether some binary black holes are dynamically assembled and in what environments and in what rates. So the gravitational waves circularize orbits very efficiently. So the isolated binaries that have been in spiraling for a long time should be circular by the time they enter the LIGO-Virgo-Cagra band at around 10, 20 hertz. But some fraction of mergers that happen in the cluster, especially these gravitational wave captures, are basically like the two black holes come close together and they are eccentric and kind of merge right away in the cluster. They don't have time to circularize. They're not emitting gravitational waves for a long time. And so those should still be eccentric by the time they enter the LIGO band. This is from a paper by Mike Zevin, yes, which shows some predictions for dense star clusters where the eccentricity, sorry, this kind of cut off, eccentricity is plotted here, and this is the probability distribution. And then the ones, you can see the ones that are ejected from the clusters have very, very small eccentricities. Oh, eccentricity is increasing down. So the ones that are ejected have very small eccentricity ejected before merger because they're ejected at fairly large separations. So they circularize by the time they reach the LIGO band. And then the mergers that happen in cluster, and especially these ones that are classified as the gravitational wave captures, have higher eccentricities. Here it's plotted against the in-spiral time. And then these eccentricity lines, this is like eccentricity at 10 hertz. I believe these are kind of the accepted thresholds for when something would be detectable as being eccentric in LIGO. So you need pretty relatively high eccentricities, bigger than like 0.1 or so, versus LISA. So I think Neil also mentioned that LISA would be able to see these stellar mass black holes much earlier in their in-spiral. I mean, only the loud ones would be seen by LISA, but much earlier in their in-spiral where they still have more signatures of eccentricity. So I think this is something very exciting for when we're actually able to get, eccentric parameter estimation for gravitational wave signals and sensitivity estimates. We can actually measure the distribution of eccentricity and compare it against these predictions. Great. Okay, so the next thing I wanted to talk about is just merger rates in general, and specifically how the merger rate evolves as a function of redshift and what that can tell us about the history of these gravitational wave events. So I must have shown a figure like this in lecture 1, but this is the merger rate density, so the number of binary black hole mergers per cubic gigaparsec per year as a function of their merger redshift. And so we infer that a long time ago at around redshift 1, the binary black hole merger rate was on order 100 in these units. And today at redshift 0, it's on order 20. And then this is the shape of the star formation rate for reference. So we can use the spin orientation statistics that I mentioned and this prediction that if we assume that dense star clusters produce an isotropic spin tilt distribution, half of the effective in spiral spins, chi effective, should be less than 0. And so now I'm switching colors on you, but in orange is the same thing that is plotted here, the total rate. And then in blue is the rate that is consistent with having isotropic spins. And so this is kind of a proxy of the merger rate that comes from globular clusters. And so you can see that it is much more uncertain because now we have to measure the spin distribution as a function of redshift, and it looks like it's below the total rate because the total spin distribution is not isotropic at any redshifts, according to this inference. Okay, so what we can now explore, what does it mean if this is the merger rate of binary black holes from clusters? Can we actually learn anything about clusters? And I guess if you're not an astronomer, maybe you don't really know what globular clusters are. Well, globular clusters are these, well, they look like this, right? I guess I already explained what globular clusters are, but they're these collections of like 1 million solar masses of stars in a 1 parsec region across. There are lots of them in our own galaxy. They probably played an important role. We're now starting to see them with JWST, for example, at very high redshift. They played some role in galaxy assembly. Understanding the connection between globular clusters and the galaxies is a very interesting field of study in like galaxy evolution. And these are also, so globular clusters, like the ones that we have in our Milky Way today, are very, very old populations of stars. So a lot of them probably formed in the early universe, but we also don't know, how many of them formed, how big they were, and all of this is really important if we want to understand the assembly of galaxies across cosmic time. So because these dense star clusters produce binary black hole mergers, we can use the binary black hole mergers that we're observing to place some constraints on the formation environments, including clusters. Okay. So one thing that is really cool about gravitational waves is that they are very inefficient at getting two black holes to merge. So there's like this time machine going on where just because we see gravitational wave mergers that happen at redshift 0 up until redshift 1, we're probing the stars that formed way before that. So billions of years before that, probably. So just because the stars were born in a cluster, for example, it can take a long time between when those stars were born in the cluster to when the black holes merged. And so this is the delay time from the formation of the cluster, including the stars in the cluster, to the black hole merger. It is predicted to follow this distribution. This is from the cluster Monte Carlo code simulation that Claire looked at in this paper. Okay, so you can look at this distribution of delay times here. It's also split up by mass. So the more massive black holes merge first, they have the shortest delay times. But for the most part, this distribution of delay times is roughly flat and log. And so the delay time is what allows us to convert between the merger rate at some redshift to the formation rate at some higher redshift. So we measure the merger rate as a function of redshift, but if we take these predictions for the delay time distribution, we can infer the formation rate as a function of redshift, or this cluster formation history. And so this is the rate in terms of number per co-moving volume per time as a function of the formation redshift, or if you like to think in terms of age of the universe, that's up here. And on this axis is just the mass density of clusters. So this is how many clusters are forming as a function of redshift, or equivalently a function of time across the universe. You can see that according to this inference, the cluster, the formation rate of clusters likely peaked above redshift 3, which is consistent with what we often think about so for comparison, here is the shape of the star formation rate, which peaks at redshift 2. So all of star formation peaks at redshift 2, but it's consistent that stars in these dense star clusters peaks at earlier times, higher redshift. The other thing we can infer is that this, just from the amplitude of this formation rate, if you integrated this across time and then inferred the number density of globular clusters in a Milky Way galaxy, for example, you would get something that is 10 times higher than the present day density of survived clusters. So that can either indicate that a lot of clusters evaporate and do not survive to the present day, or what I actually think is more likely for a lot of these massive clusters that produce gravitational wave mergers is that we simply don't see those clusters anymore as globular clusters because they've inspiraled into their nuclear star cluster and contribute to like the stellar populations at galactic nuclei. And possibly, that's related to how supermassive black holes are made. So for all of you who don't really care about these stellar mass black holes, here's a connection for you. This could also just be that other environments contribute to the this dynamics black hole merger rate. Like it could be that some of these negative chi-effective systems happen in AGN and not in clusters. So this is just an overestimate. Yes. This one?
Massive star is shorter than like lower star, which makes sense because they're more massive and the dynamics is bigger.
Yeah.
Because like in this simulation, we may take into consideration the vertical channel, because then you have to wait for the, to create a massive level, you have to do a low mass level before, and then I would expect the opening to be done as well.
Yeah, no, that's a really good question, and it is something that Claire looked at in this paper. So yeah, the idea here is exactly what you described. For the most part, for first generation black holes, the more massive ones merge first because of dynamical friction. They sink to the center, they dominate the interactions first, and only after they merge, the low mass black holes can sink to the center and do all their dynamical interactions and merge. So there's this kind of steps in the process. Actually, there's not that much of a delay between first generation and second generation mergers. Like, so if you merge the 30 solar mass black holes first and get a 60 solar mass black hole, that the merger of the two 30 solar mass black holes had to have happened in the cluster. And so that happens really quickly. You can even see that actually from Mike Zevin's plot here, where the mergers that happen in the cluster, again, the in spiral time is increasing in this direction. So the mergers that happen in the cluster happen much, much faster than the mergers that happen like outside of the cluster because they've been ejected. So if your two 30 solar mass black holes merged in the cluster so that the 60 solar mass black hole could go on to merge again, that 60 solar mass black hole is actually born very, very quickly in the cluster's history. And because now it's the most massive black hole in the cluster, everyone else wants to merge with it. So there's not as much of a delay. And that's why oh, sorry, wrong way. That's why all the massive mergers here, the 40 solar mass black holes, tend to still have the smallest delay times. So, okay, cool. Let's see what else I can tell you about. Okay, I kind of said this already, but I think it's maybe worth repeating that it's kind of surprising, like I made this claim that, oh, we actually infer that the cluster formation history peaks at redshift 3. We're not actually observing any gravitational waves from redshift 3. This is all coming from binary black holes that we observe between redshift 0 and redshift 1. But there is this delay, so we are able to probe star formation, the progenitors of these black holes above redshift 2 because of these long delay times, right? Because of this like time machine. And so even though we are observing, okay, let me just explain this plot. So this plot is showing the merger redshift versus formation redshift, and then the density in these little hexagonal bins is, where our detected events live. And so we only observe things, at least so far in this third catalog with O3 sensitivity and before, we only observed mergers between redshift 0 and redshift 1. And so if you look like in this direction to infer what the merger redshift is, most of our mergers were, around redshift 0.5. But because of these delay times for a given merger at redshift 0.5, a lot of them have short delay times. And again, this delay time argument is like coming from theory. A lot of these mergers have short delay times, and so probably formed pretty close to the merger. But because there's such a long tail to longer delay times, some of those mergers came from stars that lived much earlier, up to as high as redshifts like 6 and beyond probably. So we're already learning about the redshift 6 universe from stellar mass black hole mergers, which is pretty cool. So for example, we can learn about globular clusters. We can just generally learn about the progenitor stars to stellar mass black hole mergers at redshift 6 already. Okay, cool. I am looking at the time. Okay, I will keep going. I think I have time. I guess, does anyone have any questions on that? Cool. Okay, so I think I only have a few more things that I wanted to tell you. So I guess one thing that I wanted to highlight is that so I've kind of been making this argument that gravitational wave mergers, these CBCs, are telling us so much about stars and their environments across cosmic history and, about supernovae. But I think it's also really important to stress that these gravitational wave sources make up such a small fraction of stars. It's really just probing the tip of the iceberg. It is so, so rare for a star to be a massive star, let alone to participate in a gravitational wave merger throughout its life. So I think for a lot of kind of the future of gravitational wave astronomy, we have to make connections between gravitational waves and other systems that are related to gravitational waves, maybe slightly divergent on the evolutionary tree, but are not so extreme like gravitational waves are, if we want to get the full picture of what stars are doing, where they live, all that stuff. So there are ways that people are starting to connect gravitational wave and electromagnetic observations beyond the most popular, like multi-messenger astronomy, which we all know and love, where you actually have a gravitational wave and electromagnetic observations or neutrino observations from the very, very same source, because we've only had one example of that so far, but there's so many more connections we can make between gravitational wave and electromagnetic astronomy. Okay, so one example of this is the connection between long gamma ray bursts and binary black holes. And so long gamma ray bursts are a gamma ray burst that is essentially, this is one picture of it where you have, so the idea behind long gamma ray bursts is that they are not the merger origin gamma ray bursts. They are probably formed from collapsing massive stars. So one model for how you get a long gamma ray burst is this collapsar model, where you start off with a massive star, which you can maybe see the outline of here, and then that star collapses makes a black hole at the center, and then if it's rapidly rotating, you have this accretion disk that is falling onto this black hole, and the rotation of this black hole at the center drives this jet, and this is the GRB jet that we observe in gamma rays. And so we think that long GRBs are connected to the birth of black holes, possibly spinning black holes. And so that is the connection between long GRBs and black holes. Long GRBs are telling us that, probably a black hole was born. So if we can measure the rate of long GRBs, if we can measure that rate as a function of redshift, maybe that is telling us, when black holes are born. And so maybe that's tracing when the black holes are born, and we can compare that to what the merger rate of gravitational waves is. And so just to make this more concrete, back to Shanika's cartoon, in the isolated binary evolution case, actually a lot of people have imposed that in order to get enough spin in the stellar core that it can power a long GRB, you need to be in a situation like this, where you have a star, the progenitor star, that's in a close binary with this firstborn black hole, and then you get this whole tidal spin up scenario, which I've talked about a couple of times already. And so maybe the long GRBs are found or created in scenarios like this, where you already have a black hole that's born next to another black hole. And so this is maybe just actually a natural place in the evolutionary histories of binary black holes where you can form long GRBs. And so one thing you can just do, which one of my undergraduate students, he's actually graduating and going to a PhD program at UNC, Tom Wu, looked at comparing the rate of long GRBs as a function of redshift, or equivalently time, that's here in orange. Compare that to the binary black hole merger rate, which is shown here. And the scales of this is actually different. So for the orange curve, you should be looking at this y-axis. This is the long GRB rate per co-moving time volume, and this is the binary black hole rate. And so if you take the long GRB rate and say, okay, these are formed here, and we have some predictions for how much time happens between this and when we get the binary black hole merger, right? This is this delay time distribution, essentially. And if you just take different delay time distributions and convolve your long GRB rate with those delay time distributions, here it's power law delay time distributions with a minimum of 10 million years, and then some different slopes here of your power law. You'll get these different predictions for what the shape of the binary black hole merger rate should be. You can see that the shape here in this dashed cyan line matches pretty well the shape that we measure for the binary black hole merger rate. And this happens to be the power law with slope -1, or like the flattened log distribution, which for some weird reason, like all of the formation channels kind of predict like this delay time distribution. And so it actually looks like if you just compare the shape of the binary black hole distribution to the shape of the long GRB rate as a function of redshift, which was measured by people who work on long GRBs, this Girlanda and Salvatierra paper, you get a shape that matches. It seems consistent that long GRBs at least are telling you how many progenitors to binary black holes are forming as a function of redshift. And then there's this delay time distribution consistent with theoretical predictions. But the binary black hole merger rate is an order of magnitude lower than what you would get if all long GRBs produced a black hole that went on to become part of a merger. So not all long GRBs go on to become binary black hole mergers. Cool. Are there any questions about GRBs? Oh, yeah, sorry, it's just a different axis. So the long GRB rate, so convolving the long GRB rate with this flattened log delay time distribution will give you a merger rate that's like 200. And the actual black hole merger rate, you have to go over to this axis and it's like 20. So yeah, sorry about that.
How do you get it beyond like redshift over thing? So therefore, like the luminosity falls off very steeply after like for long years.
Oh, like where does this information come from for the long GRBs? I think so. They are in this paper. They do fit this to some parametric model. So I don't actually know where, like, I think it could be that a lot of this highest redshift information, I would guess, is driven by the prior, because I think they're just fitting like what is the kind of slope here, and then where the peak is, and then some slope here, and then this is probably an extrapolation. Oh, yeah. Great question. No. Yeah, so it is, I mean, yeah, that is, yeah, that's I guess for people who aren't aware, so there, like traditionally there have been these two types of GRBs, the short GRBs, which, come from neutron star mergers or maybe neutron star black hole mergers, and the long GRBs, which come from collapsing massive stars. And we always knew that that distinction was like completely arbitrary. People just plotted the duration of the GRB. And if you do that, you kind of see there are like two peaks that definitely have some bleeding between them. And if you like draw a line between those two peaks at like 2 seconds, you can distinguish long GRBs and short GRBs. And we always knew that classification like didn't really make sense, or it wasn't like it was an observational thing and not a progenitor thing. But recently there have been some, I think, pretty surprising, like very long GRBs which have associated kilonova with them, and so seem to be the merger origin long GRBs. I think I actually think that for most of the ones they used in the sample would have had associated supernova with them, or it would at least have been bright enough to probably be mostly from the collapsar channel. But I think people are definitely actively working on trying to distinguish the rates of merger origin versus collapsing massive star origin GRBs. And we did not think about that here, but I think there's a lot of exciting directions to look at there. And yeah.
Is there any way to record the stage of these binary blocks from the long GRB? Because we want to put into like GRB, we need a very tiny string black hole. So I was wondering like if there could be any correlation.
Yeah, that is a great question. So that's also something that Tom looked at in this paper. If you just take the fraction of black holes with large aligned spins, how does that compare to the rate of long GRBs? The rate of binary black holes with large, especially kind of aligned spins, is very, very small. And so then it's like, well, it seems, it's an even order of magnitude smaller. But there have been some papers recently. I know like Or Gottlieb had a paper on this, for example, that maybe long GRBs don't actually make spinning black holes due to two reasons. One is maybe you don't actually need that much angular momentum to power the jet. And then the second reason is that perhaps the process of launching the jet is actually very efficiently spins down the black hole. So you are actually left with a pretty non-spinning black hole. But yeah, cool. Okay, I think I just had one more connection I wanted to make. So yeah, I think another exciting new population of stellar mass black holes and neutron stars is coming out of the Gaia data. And so Gaia is able to find neutron stars and black holes in very wide astrometric binaries with usually like solar type stars. And so this is a very, very different population from the case where we have two black holes that merge with each other. Right here we have a black hole with a faraway low mass star that's never going to become a black hole, or a neutron star in such a binary. And so far there are like 21-ish neutron stars that have been found in these Gaia binaries. And this is from like a paper by Karim Al-Badri from a year or two ago, and a couple 9 solar mass black holes, also a 33 solar mass black hole, and there's also another candidate, G3425, from a paper by Wang et al. From like a yearish ago, which is like a 3 solar mass candidate. Anyway, just the last thing I wanted to say is that I think it's super, super interesting that Gaia has found neutron stars, 9 solar mass black holes, and a 33 solar mass black hole that lie exactly where we observe peaks in the gravitational wave mass distribution. There's not enough data to read too much into this yet at all, But for example, if you just focus in on the low mass part of the mass distribution and look at the component neutron stars and black holes and gravitational wave events, then you can fit something like this. This is actually not like the best mass distribution. Really, we do have a peak, another peak at like 9 solar masses, right? But there's kind of this dip maybe between them. This is often called like the lower mass gap between neutron stars and black holes. In the Gaia sample, if you don't include this event just because it was found by a different group than the other ones, then you actually get a very strong gap between the neutron stars and the black holes. If you do include it, then you get something that's more consistent with the gravitational wave mass distribution. But anyway, I think this is very interesting to look into and try to understand what are the reasons for the similarities and the dissimilarities in these two mass distributions, and how could that point to differences in the evolutionary histories, and then that can also help us figure out what aspects of the evolutionary histories are creating what features in the neutron star and black hole mass distribution. So for example, if like these distributions do end up being exactly the same, that would be kind of nice, because then maybe it's all just supernova remnant mass function or just like an evil cosmic coincidence. But yeah, I think there's a lot of exciting directions in just comparing different populations of neutron stars and black holes found in different systems. Okay, so just to conclude, so in the 3 lectures, the first one, if you completely forgot it, we talked about binary black hole population inference, so how to infer merger rates and shapes of population distributions using parameter estimation samples and sensitivity estimates. Then yesterday, we talked about the astrophysics of binary black hole formations and some of the physics that's involved in the formation channels. And then today I gave you a very small, very biased fraction of some of the emerging lessons that are emerging from LIGO Virgo Cabra's black holes and their astrophysical implications. So I think I left like 5 minutes for questions. So happy to take some questions before the coffee break. Oh, yes.
I thought like all channels predicted like metallicity would be much higher than like other places, so you would expect much lower like the number density of black hole. But like so, it would be like a very surprising thing if the number density comes out to comparable. Are the channels which predict this?
Yeah, you mean like just the fact that the ratio of this and this is so similar? Or like, yeah, I guess like what's off this plot, which is the ratio between 9 and 30. Yeah, I mean, it would be very weird. I think there is, so the 30-ish solar mass black hole in the Gaia data, and that was just an early release from the 4th data release. So it's not, could be a lot more black holes in that sample that would completely throw off this ratio. But something that's interesting about that black hole is, and that is actually really, really great with Gaia observations, is that because there's a star there that we can see, we can measure the metallicity of the star. And so we know that the 33 solar mass black hole came from a very low metallicity environment. And so again, like, shouldn't read too much into this because it's one event, but it is intriguing that it came from a low metallicity environment. And so maybe there is this, 9 solar mass black holes come from like solar-ish metallicity, and 30 solar mass black holes come from low metallicity. And then it would be pretty weird if the metallicity distribution in the Milky Way was the same, or yeah, I mean, I guess, right, like I guess naively expect that binary black holes are probing a much wider range of metallicities because they're coming from such a wide range of redshifts compared to the black holes we can find in our galaxy, but at the same time, the black holes in the sorts of binaries that Gaia is sensitive to could be like very, very old. Like they might have just formed at like they are very, very long-lived systems. So they maybe could have, traced the same metallicity evolution of the universe as gravitational wave mergers. But yeah, it would be weird. I think if everything was the same mass distribution, like that would probably be the hardest thing to explain because there's so much complicated astrophysics that goes into setting the mass distribution that, like, why would it be the same in different systems? Okay, any other questions? Cool. Oh, yeah.
What if I when you said that there's a transition, like you also should expect like there to be some peak in the mass function at that point, right? Because you're transitioning from some
Yeah.
channel regime to the cluster channel or hierarchical channel regime.
Yeah.
I guess maybe the data is not enough, but is this what you expect also?
Yeah, so it is kind of hard because there's this peak here, but it is like in Tom Collister's paper, they with this autoregressive process, they do say that kind of the best like parametric approximation to this mass distribution is a broken power law with two peaks. So like this power law is definitely steeper than this power law. So it does seem like there is some steepening here. But again, I don't want to get in trouble with the stellar evolution people and say that this is the pulsational pair instability peak, and then it gets steeper like right after that peak. But yeah, I think there is, it does seem like this part of the mass distribution at least looks different from this part of the mass distribution. Make of that what you will. Okay, great. I finished exactly on time, I think. So time for coffee.